My topic for today is not too much of technical. We'll be touching or going through a little bit of overview of two of the ongoing projects which we are doing now, right now. So one of them is a footover bridge, which is not exactly a footover, conventional footover bridge, and one of them is a solar dome. Again, it's another common feature which is coming up in India quite well. So these two topics, we'll be just going through a little overview of how we did the steel, how we dealt with the steel part and why the architect went onto the steel thing. So in the concept of a smart city footover bridge, they have changed the concept of a footover bridge to not just a footover bridge, but they have so that the bridge attracts crowd. You don't need to force the pedestrians to cross over the footover bridge. You want to attract the pedestrians to stay there, spend some time, and then cross. So Bhubaneswar actually took the step of doing this, and the Bhubaneswar government, I don't know whether you're aware of that, they are converting a huge part of the city into a smart city concept, of which one of them in the infrastructure is a footover bridge. So what it essentially does is it reduces the pedestrian crossing through the road. So it reduces the traffic volume or traffic reduction in the traffic speed due to your the pedestrian crossing the roads. Number two is that it actually attracts revenues. These footover bridge just doesn't have people just crossing. It actually attracts people to stay there, spend money, have a good time, and then come, get to the other side. It's a different concept. And that's why we call it multifunctional footover bridge. This one, it has two components. The side components are little close to what a retail mall would be, with some local vending, single-handed vending shops over there. And the central portion consists of three segments. One, the conventional footover bridge. Number two, it consists of a restaurant or a food court just above that. And number three, it hosts a huge amount of big LED display for the traffic without disturbing the traffic flow. So that's how they have designed it. This is what a conventional, it looks pretty glamorous. Sorry. So this portion, I don't know whether you can see the laser light. This is your side building. And this is actually a night view of how it is actually going to look like once it's up on the field, the construction is going on. And by the way, it's in a very congested area in Shahid Nagar, where the space to construct, you don't have much space to store the material, construct, or fabricate over there. So you need to do most of the work off-site, come here, erect, and move on. And you cannot stop the traffic over here because it's a very heavy traffic. It hosts an office ongoing traffic every day. So these buildings were, you have a girls' college on the left-hand side, and you have a whole lot of shops, along with the utility systems going to underground, and you have multi-storied buildings on the right, and you cannot shift either of them. It's very dense. So the whole challenge was to make sure that even the foundation system did not disturb any of the underground resources or any of the underground systems. So what we did was initially, when we planned, we not only sit with the architects, we sat with the civil contractor, which was finalized before the project. We sat with the fabricator, who was also finalized before the project. Why? Because I needed to know what his constraints were, how he could help me erect this central footover bridge without disturbing the traffic, and how he could do this without storing much of a material on site. So once he was quite sure of what we wanted, and he gave his feedback, our next system, our next connections, our next system, the lengths of the column, the lengths of the beam, where we would place the columns, how we would access that, was all planned. Now what we do is in most of our projects, we use something called the BIM, the Building Information Modeling, but we don't only use the static BIM. We use what we call the dynamic BIM, that is we not only create a building information model which just shows you the information, but we also create something which will show you how the structure will come up. I haven't embedded the video over here, but we have a video in case someone's interested can contact us. So the architect had this whole concept. This is how exactly the inside of the site building would be looking like. It's more of a corporate space. You'll have local vendors sitting on the ground floor. You'll have a column-free space over here. You'll have vending shops beneath the staircase. You'll have a first story a shop over there, which can be accessed from inside, from any floor. You have an escalator, you have a stair, and you have an elevator. You have all the three. Now, once this was done, this concept of this curvilinear thing was actually conceived by the architect, and he really wanted me to understand whether we can actually go ahead with this. And I actually wanted this to go ahead because this was the first of its kind in India and first of its kind in the smart city concept. This is actually how an entrance would look like. Though I'm just we'll be talking on the steel portion, but just to give you a feel of what the actual foot-over bridge would look like. This is the entrance, and you will actually be having a sitting zone in the foot-over bridge area. So that actually people can sit and even just watch the traffic and you just have a chat on that. So all the loadings of such things have been taken care of. Now, so once this whole architectural thing came up to us, the next question was, what are the structural challenges we came up to? Number one, the minimum substructure disturbance. As I told you, there are a lot of utility systems, a lot of existing foundations, boundary walls of colleges, boundary walls of shops. So we needed to make sure that we needed to disturb any of these. We could not disturb any of these foundations. We have to dig with sheet piling without disturbing these things or without letting the soil cave in from the side. Then it was called the zero rerouting of the underground service. So we were not allowed to reroute the underground service. So whatever foundation, eccentric, extreme eccentric, whatever needed to be done has been done in order to just to accommodate all of the foundation systems. And we haven't gone, all the foundations have not gone below the existing ones. Some have, so we have a multi-level foundation system over here. And some of them are actually integrating again with the existing drainage systems also. In fact, we have used the drainage walls as the wall boundaries for some of the foundations. Then in Orissa, it's a very high cyclonic zone. So when you have a 45-meter span bridge, you have to make sure that it sustains a super cyclone wind speed. So that's that was pretty challenging. And especially when you have a restaurant on top, you're not letting the wind flow through, then you're having a huge, it's like a covered conveyor belt gallery. So you have a huge amount of load coming in from that. Then we could not put bracings. I mean, the architect didn't want the bracing. So what we did was we created Virendal girder system. The whole 3 deck acts as one single beam. You have 3 different decks, but it acts as one beam. So the whole system is one beam. We have portals, we have combined moment connection, but no bracings. Okay. So we have maximized the space in order because there's a 5.7 meter walkway which they required. They wanted an unobstructed view of the whole road of the whole city. We've given that, and we have made sure most of it, 95% of the fabrication is off-site. Everything will be brought to site, erected, gone, with minimum disturbance to the traffic. And the minimum traffic interference system. Now this is how actually the whole system looks like. You have it's a very simple system. You have the side buildings, and then you have the central system. You see there's only 2 bracing systems on the top. That is mainly to host the LED display, which is a cantilever display over there. It doesn't have too much support because we needed people to walk through. Then you have that's a lower deck is for the pedestrian, the middle deck is for the restaurant, and the upper deck is for people. It's like a roof system. It also hosts a LED display. The side system, we have the building, we introduced the bracings. We didn't want, because in a system of steel structures, the more you brace, the lighter the structure, the lighter the columns. That's period on that. And the deck over here, this is the plan of the deck. You would probably ask me, by the way, this is a composite deck. with the metal system, metal composite deck and shear stud. Then someone could ask me, why do you want to put bracings over there? So what happens is, when you have a deck, it acts as a lateral diaphragm. You don't need bracings. The whole point of bracing is that when the whole thing is erected and when the concrete is not there, at that point of time, if there is a wind, if there is a cyclone, there is no way to resist it because the concrete is not there. So minimum bracing systems have been provided in just during that stage between the final concreting and the initial erection. So an effective deck system looks something like this, but what we don't do is, I don't know how people work, but whenever we use decks, we ask the contractor what company deck system they're going to use, because every deck has a different span. Some have 960, some have 970, some have 976. So in that case, the lower portion of the deck, that is the trough, not the crest, the trough should have the beam below and not the crest. When you have a crest, beam below the crest, for something like this is an ineffective composite beam. The beam is ineffective, the beam design is ineffective, and whatever design beam depth you have saved during a composite construction doesn't work. So it's very necessary for you to have the beam below the crest, I mean below the trough. So generally, beams below the crest should be avoided. So next, this is a brief on the decking system we generally follow during construction. You see this stud over here, as Mr. Hariom Gera mentioned, that there is a ferrule. It's called the ceramic ferrule. The whole purpose of that is to restrict the entire welding or the entire sparks within that thing, melt the stud bottom, and then and weld it with the beam. Mind you, while doing that, this metal decks are all galvanized. So you have to make sure that the galvanized metal deck doesn't open up too much. Otherwise, it's gone. You cannot re-galvanize a metal deck. It's not possible. Then there are some basic distances from these ribs, on the bottom ribs, it's necessary to maintain. So we have the studs should be at a 30 millimeter distance from the deck ribs. These are standards, and these are necessary to be followed inside to have an effective composite action. Next, so I've just given you an image of what exactly a staggered shear stud system, a staggered shear stud system would follow, or a double shear stud system would follow. Coming to the next part, see, a composite deck, any deck follows a one-way beam system. It doesn't follow a two-way beam. The slabs are never two-way. It's one-way, right? And the metal deck is the bottom reinforcement. That's the main reinforcement. So the top reinforcement is because of either you can give a distribution reinforcement, or if the fire code says a minimum distribution requirement is there. So that 8 mm with a 150 dia, 150 center to center, or a 8 mm with a 200 should be sufficient as a distribution reinforcement. You don't need any other reinforcements. So a metal deck generally spans one way, and that's how the shear studs. So effectively, the shear studs don't need to be in all the side beams, four side. It can be on two sides, and the minimum shear stud can be on the other two sides because it's a one way. This is how a shear stud system actually looks like. And the welding is done in this way. I hope this is the right slide. Okay. Yeah, so this is, you've already seen in Mr. Hariom Gera's slide, so we'll just skip this. What we do is that before any construction, we ask the metal deck vendors, we give them the AutoCAD drawings, the CAD drawings, and we ask him to place his decks according to my beams. And based on that, he will mark each and every deck where it's supposed to be, and those decks are to be placed at that same particular location. You can't have metal decks on site and just randomly place. It doesn't work like that. You'll be wasting a lot of deck space, you'll be wasting a beam action also. So the decks have marking. It comes like one of our projects, it came like MP01, that they have the length of deck and then where to place them. This, just that, excuse me. Is this the latest slide which we are using? Little features of the FOB. I think there was a little bit confusion regarding the presentation. So it's a 45 meter length with a 5700 meter width of FOB, and it has a central leg. Now, in the central portion of the footover bridge, we introduced columns because there was a green pathway through that. Now, initially we had introduced a 2-column system over there. But then what the fabricator told me is that when they are going to erect the footover bridge, they're going to erect it in 2 parts. They can't erect the whole thing in one. So it is better, once they have to erect it in 2 parts, it is better to have 4-column systems. That means, I'll just show you when it comes to the next slide. So that when it comes to the 4-column system, so that, you know, one half can be erected at one go independently, another half can also be erected independently, and the central portion can be joined later. It has a 2-tier FOB, utilizes the Virendal girder system which I mentioned. It has a composite deck, and the inner frame is purely made up of rectangular hollow sections. So this is how the whole thing looks like from side. You have this, the lower deck is just for the entrance portion. Then you have the middle deck for the pedestrian, and then you have the roof, the restaurant deck, and then you have the roof deck. By the way, in the roof, we do not use embossed profile sheets. We use plain profile sheet with tapping screw with no shear studs. It saves your steel and it saves your cost. So this is the erection schema of how we do the erection over there. So the first is that it's a symmetrical erection. The first part is erected. The side building is erected first. That's a stabilized rectangular building. We utilize that for erection purpose. The next part is the central 4 columns. That's it's marked in 2. Once the 4 columns are up, then comes the truck, or there comes the crane boom at the middle of the night, coming with this whole 3-deck bridge, Virendal girder, installing inside and moving off. So now you just have a steel frame, nothing else. We've gone through this. So, you know, when you are actually placing a steel deck, some of the cutting needs to be done at site. And while doing that cutting, see, this is how we actually would expect a steel deck cutting to be done, and such that it cuts through the column and it doesn't leave any gap. The cutting is not too much. Otherwise, the concrete, when you're pouring it, falls to the floor below. And the advantage of a steel deck is that actually if you have a strength of a concrete, ready mix concrete coming in, you can actually cast 2 floors at the same time. You don't need to cast each floor at a, you don't need props. This is a typical beam system. We've just analyzed, this is the span of the beam with, where it goes for reinforced concrete, post-tension, integrated beams. It's just over the period of time, that's what we realized. This is how the beam system works. This is the erection system. I know. Erection system, and we will not go through in details in this. One thing, in a beam system composite thing, if you are not giving a temporary prop, it is always better, if necessary, to give a camber in the beams. All else, because in green concrete stage, where it has not developed a composite action, there could be a deflection of the beam. If you give a pre-camber, you will not undergo that deflection. Let's go and try this. Okay, the second one was solar dome. I'll just go through this in as fast as possible. This is actually which is coming up in Calcutta. This does not have any electrical grid system or CAC supplying power to this. The entire, whatever museum, amusement parks and every buildings are going to be built within the dome are going to be powered by these solar panels only. That's it. So this is the West Bengal government is the client, and we had the project consultants, and we were the structural consultants for this. So we'll just skip the architectural note on this. The basic framing of the dome. So this is not exactly a hemispherical dome. It actually extends 12 degrees beyond the hemisphere. So it's 12 plus 180 plus 12 degrees. That's the curve of the dome. Next, there's a viewing gallery. The glass connects the outer frame. So there are two frames over here. One is the main core frame which holds the whole structural stability, and second is the frame which holds the glass and the solar panel. There are glass facading also in this. This is how actually we've used the 3D software Tekla for this. This is how actually the dome looks like. The columns are built up plates, and the beams, wherever possible, are either built-ups or hollow section, Tata structure or hollow sections. See, if this is a curve of a column, see the trouble. I'll just tell you three conditions. We've just covered three of the constructional troubles, not troubles, apprehensions we had to get done before we did the detailing. You see in this, I've showed you an image of the column lying on the ground for fabrication. When you're doing a fabrication of a box column, the weld of the joints have to be on the shorter side of the box. It cannot be that it cannot be on the top and the bottom, because you can weld the top, but you can't weld the bottom. So when you place the weld, and then you put the short plates, and then you put the cover plates. So you have to make sure where the weld is, and accordingly the design is done. Because this column is going to be fabricated on the ground, and then you're going to erect it up. So this is the first stage sequence of the column. When we do that for a dome, the first stage is the first hemispherical grid. When you do that, you have guy ropes to sustain this. Otherwise, this doesn't stay in place. You have guy ropes and others to sustain it. Then comes the perpendicular grid. Once you do this, this is now a stable system. You don't actually need a guy rope, but then for constructional purpose, they can provide, because Bridge and Roof was a major contractor. They have the resources to provide a guy rope to sustain this. Then comes the annular ring. This annular ring actually has a number of columns terminating to that. So there are two levels of annular rings. So after putting the annular ring, then you have the other set of columns, the remaining columns which are going to terminate an annular ring. You fabricate those and then directly weld them to there. We are not doing any plate connection. We are directly welding it to each member. Then comes the second annular ring. Once the second annular ring is erected, you have few other columns coming and terminating at the second annular ring. Once that is done, now you have the whole dome in place. This is a splice connection. In a splice connection, we made sure that all the 4 plates don't have the splices or the cuttings in the same plane. They are in different planes. The top and the bottom plate has a horizontal splice, and the side plates have a diagonal splice. The shear and the load transfer are far more safer than this in this sort of system. So once you do that, you'll see these splices are not at these columns, by the way, they are not the same section. The bottom portion was 900, then the depth came up to 750, then 400. So we don't put the splices at the joints. So we put the splices 1 meter or 800 millimeter above or below the change of columns depth. The challenge over here, one big challenge is, how do you actually, once you have the columns up, how do you actually erect the beams, the bracings? You have a cross bracing, it looks like a cross bracing, but how do you erect them? Because because you can't just put a beam like this. So what we did is, we needed a gusset plate to erect it, but then that also we followed a methodology. See, what we did was, once the columns were up, the columns come in with the gussets, the yellow plates are the gussets. Once that is done, one of the bracing member is a full length member, and it's first brought in a diagonal shape. They have a central slit opening in the hollow section, and you just put it in. Weld it at the gusset, one member is done. The next thing is that, by the way, you still don't have the bottom chord and the top chord over here, because you need to put the members from below and top. A half bracing comes in, gets welded over here, gets directly welded over here. Similarly, you have the top bracing coming in, again, being put from the top, slided into the gusset, welded at the gusset, then welded directly over here. Now you have a bracing system up. From the lower end, put the bottom chord members. From the upper end, next you have the top chord member. Now your bracing system is intact. You can erect the bracing in such a fashion. There is no other way you can do a bracing for this dome. Now, just outside this main frame, there is a smaller grid of hollow section, a dense hollow section directly welded into each other. And that is actually going to host the glass also. Now for this actually what we did not only do, because this hollow section is going to experience thermal expansion and contraction. And that's where actually if you don't take care, the glass is also cracked. We've experienced this in Kolkata airport. I've seen the glass facading failing because of that. So what we did, the glass actually we designed a connection, actually a glass connection to a steel member at each of these glass joints, so that whenever there's a thermal expansion and contraction, the glass connection takes care of all the expansion and contraction. The glass is always safe. So this is the basic grid, again the hollow section grid, the glass frame grid on the main frame, and that's how it's going to look like. So it's just coming up in Kolkata. I hope to see it soon, though it's running behind schedule, but thank you very much for listening.